Hello, welcome to the course Excelling with Mathematical Modeling. Today we will be talking about kidney function model. Now it is not a general kidney function model, but we have taken a typical problem that is related to this kidney function. So let us move on to the problem. So let me write it point-wise. The first point is, say, kidney filters out 45% of vitamin A in the plasma. Number 2, each day. The liver absorbs 35% of vitamin A in the plasma each day. Number 3, 2% of the vitamin A in the liver is absorbed back in the plasma each day. Next one, 15% of the vitamin A in the plasma is converted to some chemical B. 5% of the chemical B is converted back to vitamin A in the plasma. 10% of the chemical B is filtered out by the kidney each day. Now, with so many information, if you want to formulate a model, what you have to do is you have to rely on schematic diagram first. So it is also better that if you visualize this whole information in a chart. So I have, say here, say vitamin A in the plasma, this is vitamin A in the liver, and this is the chemical B. To make it interesting, change the color. So this is vitamin A in the plasma. This is vitamin A in the liver. Let's put it as Pn. This is at L, and this is chemical B. So let it Bn. And then let's see various relations. So kidney filters out 45% of vitamin A in the plasma each day. So 45% goes out, which is 0.45. Then system. Liver absorbs 35% of vitamin A in the plasma each day. So the liver absorbs 0.35 of vitamin A in the plasma. This is done. 2% of vitamin A in the liver is absorbed back in the plasma each day. So 2% goes back, so 0.02. 15% of vitamin A in the plasma is converted to chemical B. So 15% goes to chemical B, 0.15. 5% of chemical B is converted back to vitamin A in the plasma. So from here we have 5%, 0.05, and 10% of chemical B is filtered out by the kidney each day. So you have 0.1 which is filtered out. Suppose in addition to that I have two more information which says that daily intake of vitamin A in the plasma is 2 mg and daily intake of chemical B is 1 milligram, 1 mg. So now we have this complete model and the variables are Pn, Ln and Bn. Let's now form the equations. Okay, so I already have the diagram. So say Pn, Ln and Bn. This is Pn minus 1, Ln minus 1, Bn minus 1. So what you have to look into that from this what is going out and what is coming in. So going out is 0.45, so minus 0.45 Pn minus 1. Then 0.35, so minus 0.35 Pn minus 1. And then plus 2 mg, which is also a direct input. I'm coming to the other terms later. Now let's look into the liver. So this 0.35 is added to the liver, so it is plus 0.35 Pn minus 1, this term. And 0.02 is going to the plasma, so minus 0.02 Ln minus 1. And this goes to the vitamin A in the plasma, so plus 0.02 Ln minus 1. Next come to this, the chemical B is 0.1% going out, 10%, so 0.1 times Bn minus 1 goes out, then 0.15 is coming in. So from here minus 0.15 Pn minus 1 goes out to chemical B, so plus 0.15 Pn minus 1. And from B there is 0.05 of the chemical is going to the vitamin in the plasma, so minus 0.05 Bn is added here to 0.05, sorry, Bn minus 1, Bn minus 1, and 1 mg of intake, so plus 1. So this becomes the whole model. So if I just go through the model one more time, it looks a bit complicated, though if you remember it stepwise, that this is the amount of the vitamin in the plasma at time n, this is at n minus 1, and then you see what is going out and what is coming in. So let's first see what is going out. So one is this 0.45, so 0.45 is going out, then this 0.35, so 0.35 is going out, so that's why both are negative. Then a constant input 2 mg, so that has been added. Now another 0.15 going out, so this is also 0.15 going out. Now let's come to the liver. Here 0.02 is going out, so minus 0.02, and it is going to the vitamin A in the plasma, so here is the term, and 0.35 is going out and coming to the vitamin A in the liver, so from here it has come here, and then go to the chemical B. In the chemical B, 0.1 is filtered by the kidney, so here it's 0.1. Then from vitamin A in plasma it is adding to chemical B, so plus this is this minus and it came here, so plus. Then from the chemical B, 0.05 is going to vitamin A in plasma, so this is going and it is being added here, and plus 1 is the constant input. So once you get this, then we have to look into the equilibrium solution and the stability analysis. So if you go for the equilibrium solution, then I have to replace Pn and Pn minus 1 by some P star, Ln and Ln minus 1 by some L star, and Bn to Bn minus 1 by some B star. If you do that, you will get P star equal to P star minus 0.45 Pn minus 1, 0.35, sorry, P star minus 0.15 P star plus 0.02 L star plus 0.05 B star plus 2. So this and this cancels, and if you simplify, you will get 0.02 L star plus 0.05 B star minus 0.95 P star equal to minus 2. So this is one equation. The second one, which is Ln equal to Ln minus 1 plus 0.35 Pn minus 1 minus 0.02 Ln minus 1. So I replace these two by the corresponding equilibrium symbols. So this and this cancels, and this gives me L star equal to 0.35 divided by 0.02 P star. So this will give me 17.5 P star. So I get L in terms of P star. The third equation, Bn, is equal to Bn minus 1 plus 0.15 Pn minus 1 minus 0.05 Bn minus 1 minus 0.1 Bn minus 1 plus 1. So this is replaced by B star, P star, this and this cancels, and I will get, after simplification, B star is equal to 1 plus 0.15 P star divided by 0.15. So I will get 6.667 plus P star. So this is my P star. So I got L in terms of P star, I got B in terms of P star, and I will substitute it here to calculate the P star. So if I do that, I have the equation 0.02 L star plus 0.05 B star minus 0.95 P star equal to minus 2. So I substitute L star is equal to 17.5 P star from here, and B star equal to 6.667 plus P star plus 0.05 6.667 plus P star minus 0.95 P star equal to minus 2. And the simple linear equation, if you solve, you will get the value of P star to be 4.24. And similarly, your L star will be 17.5 into P star, which is equal to 74.24, and your B star is equal to P star plus 6.667, 4.24 plus 6.667, and this is 10.91. So I have the equilibrium points 4.24, 74.24 and 10.91. P star, L star and P star. Let's now look into the stability analysis. So if we rewrite the model after simplification, you will get this is 0.05 Pn minus 1 plus 0.02 Ln minus 1 plus 0.05 Bn minus 1 plus 2. Ln is equal to 0.35 Pn minus 1 plus 0.98 Ln minus 1, and Bn is equal to 0.15 Pn minus 1 plus 0.85 Bn minus 1. So the coefficient matrix 0.05, 0.02, 0.05, 0.35, 0.98, 0, 0.15, 0, 0.85. Now, once you get the coefficient matrix, you have to calculate the eigenvalue, that is determinant of A minus lambda I, and this will imply 0.05 minus lambda, 0.02, 0.05, 0.35, 0.98, 0, 0.15, 0, 0.85. So this is a bit complicated, though you can do it by hand, and you will be able to find the values of lambdas to be 0.99, 0.86 and 0.033. So the modulus of all lambda i's is less than 1 and the system is stable. Now let's use Microsoft Excel first to find the eigenvalues and then to visualize this graph. So I already have this one open, and the coefficient matrix is here 0.05, 0.02, 0.05, 0.35, 0.980, 0.15, 0.85, and here I have written the identity matrix. So to calculate the eigenvalue, we have to find the determinant of A minus lambda I. So I put arbitrary value of lambda and I first calculate the matrix A minus lambda I. For that, since this is a 3 cross 3 matrix, so first you select 3 cross 3 cells and then put an equal to. Then select this A 3 cross 3 minus lambda multiplied by I. And to get the values for all these 9 cells, you have to press Ctrl and Shift at the same time and then press Enter, and it will come. So if you see that, because lambda is 0, obviously it is going to return A, and you got this as A. If I change this value to 1, you can see this has also changed. Okay, so that's how it works. The next thing is, so I make this as 1 now. So the next thing is that this I have to calculate determinant. So this is equal to, the formula is MDET, and you will get this, which calculates the matrix determinant. So double click this and choose the matrix, that is A minus lambda I, that this much, close the bracket and enter. So, you have a matrix A, identity matrix I, you have calculated A minus lambda I, which is this matrix, and you have calculated this. Now, go to this data and click this what if analysis and then click goal seek. So, this kind of window will open. So, what is the goal? The goal is to make the determinant A minus lambda I 0. So, in place of set cell, you choose this one. So, this determinant will go to 0 by changing which cell? By changing this value of lambda. So, this cell, and you click OK. So, 0.99 is one of the eigenvalue. So, I can take another one, I just put it say 0.5. So, you have to place, since there is 3 cross 3, you know there will be 3 eigenvalues, but one thing you note, if it is a imaginary eigenvalues, this will not give imaginary eigenvalues. So, it has to be real. So, this has its limitations. So, I change this to lambda equal to 0.5. I again go to what if analysis. I go for goal seek. I choose determinant A minus lambda I, which I want to be 0 by changing this initial value of lambda, and I got that to be 0.86. So, one value is 0.99, another value is 0.86. I make it to 0.05. Again, I calculate, I click what if analysis, go to goal seek, choose the cell determinant of A minus lambda I, which should be equal to 0 by changing this value of lambda, and I get 0.034. So, I got 3 eigenvalues. Now, here is the the problem or the catch is that okay, you have to play with this a little so that you can get to the eigenvalues. The initial condition of the lambda is very important here. So, if you fail in this, getting the approximate value of eigenvalue close to the actual eigenvalue, this may not work, or this may repeat the same eigenvalue again and again. But in that case, you just have to take the help of your manual calculation. But otherwise, it's sort of a good way of calculating the eigenvalues using this Microsoft Excel spreadsheet. Next, we move to the numerical solution of the model. So, I already have the equations here. I have the n. Let me take the initial values. So, I put it 10, 20 and 5. So, this is equal to 0.05 multiplied by p plus 0.02 multiplied by the L value plus 0.05 multiplied the initial chemical value plus 2. Similarly, this is equal to 0.35 multiplied by the p value plus 0.98 multiplied by the L value, and this is equal to 0.15 multiplied by the p value plus 0.85 multiplied by the p value plus 1. So, let's drag them a little. So go to insert, go to the chart and give the chart. So as you can see that they are slowly approaching the equilibrium values. If you want to have the whole set, you just go to some, drag to some more values, say up to 100 of them. Okay, let's draw this one. So highlighted 100 values and then go to insert, go to this chart and calculate this. So as you can see that this is kidney function model, and this is, go to select data, the series 1, edit, you say V in the plasma, or you just make it short, V underscore plasma, series V underscore liver, series 3 is chemical P. So you got this visualization of the model, and the model is stable, so it is going to the equilibrium points. Now if you want to copy them, you just right click and go to copy. But here what I find is if you want to paste it in this, they will say that you have to close the Excel sheet first. So you can just close and then you can try paste here. So it will come. So as you can see that while solving the model, we got equilibrium point and all the eigenvalues are positive and their modulus is less than 1. So it is a stable equilibrium. So with this we come to an end of this kidney function model. In my next class we will be looking into some data handling or estimation of parameters. Till then, bye bye.